Hello, this is my first YouTube video. My name is Ayush and my topic is electromagnetism. So, for IGCSE, I'll be covering three topics for electromagnetism, that is, magnets, motors, and generators. Okay, so let's start with magnets. So, as you know, there's two poles of any magnet, the north and a south pole, which are named because when free to rotate, if you hang a magnet on a string and it rotates, it positions itself according to the Earth's magnetic field, according to the Earth's magnetic north. So that's how you know which pole is north and which pole is south. When two opposite poles are brought near, they attract each other. So a north and a south pole will attract each other. But if two like poles, a north and a north pole, which are brought next to each other, they will repel each other. They will push each other away. And that is the principle of magnetism. There's two types of magnets. There's a permanent magnet and there's an electromagnet. But more of that in the next slide. Over here you can see uh, the magnetic forces. Over here we have the opposite poles which are attracting and like poles which are repelling. To remember this, you could use the statement opposites attract. Over here you can see an electromagnet. So the main fundamental part of an electromagnet is that it has a soft magnetic material in it and a coil. It uses electricity to induce a magnetic field, but a permanent magnet, it does not use that. It is a magnet in itself. Its electron structure is so strong that it can attract without the need for using electricity or a coil, as you can see in an electromagnet. So there's two types of magnetic materials, hard and soft. Electromagnet is usually made of soft magnetic material like iron, but a hard magnetic material is like steel. It is used in permanent magnets, and it's much more difficult to magnetize, and once magnetized they don't revert back easily. So hard magnetic materials like steel are used in loudspeakers, microphones, basically any kind of communication devices. So soft magnetic materials gain and lose magnetism easily, like soft iron core, and are used in electromagnets. These electromagnets can later be used in many other things. For example, if you look at your fan at your home, there's a electromagnet in it. There's a motor and electromagnet. You can easily switch it on and off, which turns the motor on and off, which in turn makes the fan stop and start. So to magnetize a material, you either rub the material so that electrons arrange themselves. You rub the material with a magnet in the uniform direction, or you place it in an electromagnetic field made by a coil supplied by a battery. This electromagnetic field, the battery and the current should be of a direct current so that the electrons arrange themselves to create a proper structure from which they can magnetize. Here you can see what I just said. If you rub a unmagnetized object like a steel bar with a permanent magnet, the in a same direction, the electrons will attract to the northern part of the north pole, and then they will start forming a uniform straight structure. And over then you can see the field lines as well. Here is a soft magnetic material. Here they use an iron nail, which is a soft magnetic material, and a coil of wire. It provides a DC current, which is the direct current. It is only moving in one direction from positive to negative in a conventional flow, which is making the electrons get a uniform structure. We looked at magnetization, but you can demagnetize a material as well. You can hammer the magnet in an east-west direction, because usually a magnet, when you hang it on a string, like I said earlier, it positions itself in a north-south direction. But what happens if you turn that to an east-west direction and hammer it? It loses all its magnetic field and all the field lines. It loses its electron shape. If a magnet is losing its electron shape, that's the basic principle behind demagnetization. You could also place a magnet in an alternating current shown here and take it out slowly so that all the electrons are dissipated. They are uh, thrown about everywhere because of the change in flow of the current. Or you could just melt the magnet, which makes it lose its physical structure. in turn losing its electron structure and magnetic property. So now let's talk about field lines. Any magnet or any magnetic material will always have something called as field lines. If you magnetize an iron core, or if you have a permanent magnet or a magnetite ore, it will always have field lines. They are a visual representation of the range and strength of a magnet. You can demonstrate that by an iron filling experiment. So what happens is that you lay a bunch of iron fillings on a white piece of paper, and you place a magnet on the piece of paper, and the iron fillings align themselves according to the field lines. So like north to south, they align themselves. We use the convention of field lines coming from the north pole and attracted to the south poles in all kinds of solenoids, magnets, everything you can think of. Now let's talk about solenoids and electromagnets. An electromagnet is made by a flowing current through a coiled copper wire. The coiled part is important. It is also referred to as a solenoid. Due to this, the electric current induces a magnetic field. All kinds of wires, anything that has electricity flowing through it, always has its own magnetic field. So the reason for coiling it is because it concentrates the magnetic field much closer into the coil, in the center of the coil, and if you add a core to it, it becomes much more concentrated and much more stronger. So to increase the strength, you could either increase the current flowing through the coil, you could increase the number of turns, so more electrons are structured in a way that it amplifies the magnetic field, or you could add a core of soft iron, which increases the surface area, or which increases the strength of the magnetism. Forces of an electromagnet. So like I said earlier, you have a coil, it has current flowing through it, it has its own magnetic field. But what happens if you uncoil it? You get a straight wire which has current flowing through it. It will be a straight line with magnetic fields in circle moving in a clockwise direction. It is represented by the right hand grip rule. You can do this, you can show your thumb. Your thumb is the wire moving upwards, and over here you can see this would be the direction of the magnetic field clockwise. Imagine this as 12 o'clock and this as 3 o'clock. So the magnetic field is moving this way. If you see the wire going downwards, it is going this way, it is moving from 12 to 3. So like it is moving in a clockwise direction. It will always move in a clockwise direction regardless of uh, how you coil the wire. So this is a straight wire and there's a magnetic field around it. That's basically the right hand grip rule. An electromagnet is a much more clever way of using this property in a coil, making the magnetic field much more concentrated, and you can then use that to induce electricity or create motion. Like I said, we have a current flowing through it, and then there's this field, this magnetic field, which moves in a clockwise direction. Here is how the field lines work. They move from north pole to south pole, and then into the south pole from the north pole. Here you can see the most concentrated, the most strongest magnetic field is at the poles, at the part where there's a north and a south pole, at the end of the magnet. That's where the magnetic field is much more concentrated. So let's take a look at electric motors. An electric motor is a device which is designed to produce movement due to a current flowing through it. It can be powered using a battery, and it is very simple to build. You require two electric brushes connected to a wire, a coil of wire, two magnets, an axle, and a split ring commutator. It is used in all kinds of motion, like all kinds of motors, electric brushes, fans, power tools. You can remember the function of electric motors by relating it with the term motion, which means movement. So, and motors basically use electricity to generate some kind of movement. If there's movement taking place, it is usually a motor. So, how do motors work exactly? The current first flows in through the brushes into the coil. So if you have a battery here and a wire connected to a coil, and there's two magnets here as shown in the diagram of the textbook. Now there are two magnets, the electromagnet and the permanent magnet. The electromagnet is actually the coil itself, which is put on an axle, which gets electricity from some kind of a source, from some kind of a battery through the brushes. So it makes the coil magnetized. It becomes an electromagnet. There's a magnetic field around it. And then there are permanent magnets. There's two separate magnets which keep it in motion. So there's a magnetic field of the coil and magnetic field of the other two magnets, and they interact with each other in such a way that the north and the north pole repel each other, which, imagine this as a magnet. Here is the north pole and here is the south pole. So, and here is the north pole of this magnet and here is the south pole of this magnet. So there's north and north pole, they repel each other. But what happens when it moves into this part, it's vertical, its momentum carries it on the opposite direction, which changes the brush connections, which inverts the brush connections, which makes a south and a south pole, which then repels each other. So the brushes are replaced every half turn, and at the vertical position the momentum pushes it past that position. So when it's vertical, there's still momentum of that coil, it pushes it past, and then the brush connections are reversed, and that's how the motors keep things in motion. This mechanism reverses current in every half turn. When it is horizontal, there is the highest force, there's a highest effect of the force generated on the coil, because there's an interaction of magnetic field. When it is vertical, there is no interaction. So when it is horizontal, the largest effect of the magnetic field is observed. Over here you can see what I just demonstrated. Here is your battery source, here are your brush connections, and this is a split ring commutator. So the current flows from the commutator to point HG. HG we assume as a south pole. Then because of that they repel each other. So it moves in the direction of C, and the current flows from FE back here. But when it becomes vertical, the momentum pushes it past that position. But then these commutators are reversed, they change the direction. So now this is a new north, because earlier this was south, this was north. When they repel each other, it becomes north, and it becomes south, and here north. But if the brush connections are reversed again, the final answer would be here EF would be a north side and HG would be a south side again, only because these connections are reversed, and because of this they repel each other again, and then it can move in the direction of A. So force on a conductor. A motor produces movement because the coil experiences forces. So there is a repulsion force from between HG and the south pole, which causes a movement, meaning the magnetic fields interact with each other. It is not necessary to have a coil to produce movement. The requirements are a magnetic field and a current flowing through the magnetic field. When a current flows through a field, it produces a motion of the motor, and this is called a motor effect. So the motor effect is basically the cutting of field lines. There's a field line of HG, this as an electromagnet, and a field line from the south pole. So these interact with each other, causing some kind of a force taking place, which turns the coil. Over here you can see there's a current flowing through AB, and the magnetic field lines of AB and north and south are cutting each other, which makes some kind of a motion. So which can be demonstrated using the Fleming's left hand rule. So if you hold your finger, if you hold your index, thumb and your middle finger all in 90 degrees to each other, like this way, and hold it like this. So the forces in the motor, namely magnetic field, current and force, can be expressed through the Fleming's right hand rule. The thumb represents the motion of a motor effect. The index finger shows the direction of magnetic field in a motor, and the middle finger represents the current flowing in the motor. Let me show you with this question here, with this part here. Okay, so we have thumb, which induces motion, middle finger, which is current, and the first finger, which is the magnetic field. So like I told you before in this first slide, here We use the convention of field lines coming from the North Pole and attracted to the South Pole in solenoids and magnet. So we use that. It comes from the North Pole and goes to the South Pole. So the field line, the magnetic field is moving in this direction. Alright? Okay. The current is flowing from say F to E in this direction. So the motion is upwards. Like I said, the coil turns upwards. So this is your motion upwards. The current is flowing this way and the magnetic field is this way from north to south. And when these interact, the motion is upwards, which makes the coil turn vertical. So now you understand how motors exactly work. Over here you can see what I demonstrated. You can try it with this question as well. There's a north and south pole. It is going downwards. The magnetic field is downwards. So first finger is field. The current is flowing from B to A. So there is a motion in this direction. Over here you can see from B to A the current is moving through here. The magnetic field is from north to south, and then the motion is here as demonstrated by this diagram. Over here you can replicate this and try it with some other questions from the textbook. So electromagnetic induction. This is another concept that you need to know for your IGCSEs. You use a motor to generate movement from an electrical energy. You can reverse it to get a generator by creating movement by spinning an axle. Spinning an axle which has a coil in a magnetic field which induces a different kind of current. This is called a dynamo effect. It induces an EMF. EMF is the electromotive force. It is measured in voltage. To generate induced EMF, you either require the magnet or the wire to move related to one another, and these can be observed by connecting a wire to ammeter or voltmeter. Alternating current or AC is called so because of the bidirectional flow of electrons. This happens because the wire spins periodically and changes its magnetic polarity. So it fluctuates from positive to negative over a period of time. An AC ring, AC generator used to generate AC, which is like a reverse DC motor using slip rings. So we looked at DC motors. The DC motor uses some kind of a current to turn an axle. It uses some kind of electricity to turn an axle, and this is the interaction between magnetic field and the electromagnet of the coil, which generates some kind of movement. But in a reverse DC motor, which is an AC generator, you turn the axle yourself. You use some kind of energy from your body to turn the axle around, which cuts the field lines of the magnet. So there is no reversing of brushes here, which means that uh, the current is not direct. It is not reversing every half turn. It is not in the same direction, which means that it is changing over a period of time. Over here you can see split ring commutator. It is split here so it can reverse easily, but here's an AC with two rings, and this is a slip ring commutator. So when you turn the axle, the ring just turns around and provides EMF to the brushes. It provides current to the brushes, which is stored in a battery. Over here you can see it is flowing in only one direction, but alternating current is moving in both directions. This is because of how the coil is being turned. It is not turned in such a way that it provides only unidirectional flow of electrons. So to demonstrate how it works in an AC generator, you use Fleming's right hand rule. There's a left hand rule for motors, a right hand rule for generators. So in a generator, the direction of induced current, the force and the field can be represented by the Fleming's right hand rule. The motion and field is similar in direction. Over here you can see the motion and the field is similar, but the current flowing is different. It is always opposite to the Fleming's right hand rule. The direction of the current depends on what kind of magnetic field, or more where the magnetic field is. It pushes the field, inducing a different kind of current. So if you use a force in some different way, if you use a force downwards and there's a field this way, the current is going to flow to the right. If you use a force upwards, if you move it upwards and the field lines are towards you, towards the screen, the current is going to flow to the left direction. So it really depends on what kind of direction and what kind of force you are applying to the generator. Over here you can see there's a current in this wire. It is moved up and down. If you move the wire up and down, if the direction of the force is like this and the direction of field is north to south this way, then the direction of current will be towards you. It will flow through the wire, and that's how you generate electricity in the first place. Basically how they generate electricity in all kinds of turbines or generators is that, imagine in a hydroelectric station, water is flowing at a great speed on a turbine. It makes the turbine move rapidly, which causes this axle to move very rapidly and cutting the field lines, and that's why a large amount of EMF is generated, a large amount of current is generated, which can be later stored in a dynamo, and then which can be transported along electric power lines to cities and different towns. So that's the basic principle of electricity generation and electricity motors. So now let's look at our final topic, transformers. So it is a device to increase or decrease the voltage or current flowing through a wire. It is accordingly called a step up or a step down transformer. It includes two coils and a core. The magnitude, the amount of current which is being increased or decreased, it depends on the number of turns in the coil. So it is represented by the equation voltage in primary coil divided by voltage in secondary coil is equal to the number of turns in primary coil divided by number of turns in secondary coil. This is called the transformer equation. It always only works with alternating current, which induces an EMF across the coil, which is reduced or increased by turns in a coil. So alternating current can be generated from an AC generator. So imagine if there's a large amount of electricity being generated through a hydroelectric station, and now they want to transport it to some different place, and they need to reduce it so that maybe your kitchen appliance, if you need to use it for your kitchen appliance, it does not blow up. Imagine there's like 50 billion 50,000 volts of 50,000 volts of electricity going through a coil, and there's this transformer, but you need only say 25 volts. You need to get a lesser number of coils in your secondary coil. That's how you can minimize the effect of the electricity generated, and this can be done using a step down transformer. Similarly, if you want to increase the strength of the current, so you use a step up transformer. So here you can see there's this VP, which is the primary voltage going from the primary circuit in an alternating current. It moves from the first coil over here. Okay, imagine if this is a step down transformer and there's a lot of voltage. Imagine this is a lamp which operates on maybe 3 volts, and there's 25 volts of current flowing through it. So, and imagine there's like maybe 100 coils here, and then there's like only a few. Like if you calculate that right now, there's like 25 1/4. Here is what did I say earlier? 2 volts, no, 3 volts. So 1/4 equals 3 upon x. You need to cancel that out. You get 12, as you need 12 coils in the secondary coil to get your final voltage as 3 volts in the bulb. So that's it for the entire chapter of electromagnetism. I hope it wasn't really confusing. You can post it in the comments if you have any questions or queries about this topic, and I'd be happy to answer you.